Let's talk about adaptive integration. What is the idea? The idea can best be explained in this example. If we have this integration interval and we want to integrate here, so we want to get this area, okay, then what do? We apply, for example, trapezoidal value or Newton codes or Gaussian quadrature or whatever. And then we evaluate our function. And in this case, it's quite obvious that we have a function which behaves not in one unique way. Here, on that part, we have almost no oscillation. The function is more or less a straight line. So on this part, it would not be necessary to refine very much. So we don't need a high resolution to get good integral values. And the same is true for that part. Here we don't need a high resolution. But on this part, a high resolution is necessary because there are oscillations and we should have a very high resolution to get good values. So we want to adapt to the function. But how can we adapt? We can't do that plot because doing that plot means evaluate at a lot of points, and that would need a lot of CPU time. And so this is not an option. To generate that plot, I evaluated the function at, let's say, 200 points, and this is too time consuming. So how can we do this adaptation? And it's completely clear that for professional implementation of an integration, then there should be adaptation. Okay, so how can we do that? And surprisingly, the idea we can use is simple. And we can do it with that code. In this code, we use the trapezoidal integrator, but you can replace it by whatever you want, by Gaussian quadrature or Newton codes or whatever. So first do our integration here, in this case with only one part, so evaluate only at the position A, at the position B, and then the trapezoidal sum. Then the next line, do it with a more fine resolution. So in this case, evaluate the function also at the midpoint of A and B, and then check, is the difference small enough, less than tall? Then believe in your integral value in the second one and return this value to be your estimate, your approximation to the correct integral value. And if it is not true, then do a final resolution, but do that on each part, on the left part of the interval AB, and do it on the right part of the interval separate, independently. And then you have to halve also the tolerance. For the left part, it's enough if tolerance halved, and for the right also halved, and then in total you will be below the given tolerance. Okay, so integrate on the left part from A to the midpoint, A plus B halved, that's the midpoint between A and B, and so the first line does the job on that interval, and here integrate from the midpoint to B, so here do the job for the right hand side. And then recursively we will do that again. And so recursively it will be checked again, do we have to subdivide or don't we have to subdivide? So here I have an example. My example is the function sine of x something. This is this graph. And then I use the tolerance, as far as I remember, 0.05. And using these values, then we get the following. First, we evaluate the function here, and then this is the trapezoidal sum, so this value. Then evaluate also at the midpoint. This is the midpoint, and then do that trapezoidal value. And then you get this area and that one. And then we compare these two values, and the difference of these values is more, in this example, more than 0.05, more than our given tolerance. Okay, then we do the split. Then let's do the job on the left hand side. So first, what is the trapezoidal value if we evaluate at these 2 points? And then what is the midpoint of this value and this value? It's that. And then we evaluate also here, then this trapezoidal sum, and this is more than this tolerance halved, so more than 0.025. The difference of the two trapezoidal values is more than that, and so we have to refine once more. So what do we do? Here we have that structure, evaluate at this point, trapezoidal sum, and midpoint. Then these two trapezoidal values are less, the difference is less than this number, so we say, okay, that's okay. We don't have to subdivide on this interval more, so the job is done. Then let's do the job for this interval, evaluate at these 2 points, then take this point, compare the two integrals, it's not close enough, and so we split again. So we split, then let's compare this trapezoidal sum with that trapezoidal sum here, then it's not close enough, half of that value, then we split again. And so we split here. And now it will turn out that this trapezoidal sum and with the midpoint, this is below our desired tolerance, and here also, so we don't subdivide more. And that's what's going on. Okay, and so we get this subdivision structure. And what do we see in the end? In the end, we see that on parts where the function does not oscillate very much, we have a more coarse resolution, and in parts where we have more oscillation, we have a lot more points here. So here a lot more subdivision took place. Okay, that's the simple idea and that's the simple implementation, and as we see, it works. That's the idea of adaptive integration. What does adaptive mean? We want to adapt to the special situation. We don't want to do our job as we always do, but we want to adapt to what is necessary, and we don't want to do more than it's necessary. That's adaptation. And not only for integration there are adaptive strategies, also for solving linear systems. Remember to iterative methods. In this case you can also try to adapt. For example, for differential equations you try to adapt. You take a big step width if you can afford, and the error will not get too big, and you take a fine resolution, a very small step width if it's necessary, but you try not to take a fine resolution, a high resolution, if it is not necessary. So there's always, in all chapters about numerics, you can think about how can I implement some adaptation, and here talking about this topic in the context of integration, I gave you a hint how that can look like. Okay, this was our video about adaptive integration.